Good afternoon, and welcome to Worldwide Developer Conference. I'm Craig Keithley. I'm the USB and FireWire Technology Manager in Apple's Worldwide Developer Relations Program, and I've been working on USB and FireWire drivers and products probably for the last 4 years. I've worked on just about every different kind of driver that exists at Apple, and it's been incredible to watch the adoption of IOKit over the last year. I've worked with developers internal to Apple and external to Apple, and all of them come to me and tell me how powerful it is, how useful it is. The object inheritance model that we have makes it easy to write drivers that leverage off of the families that are in the operating system. And so to introduce this to you, describe it to you in depth, I'd like to bring up Dean Rees. Dean?
Thank you. Hi, good afternoon. I'm Dean Rees. I manage the IOKit team at Apple. And I don't know how in-depth we'll be able to get today because IOKit covers a lot of API and a lot of ground. But we'll definitely cover as much of it as we can, and there's a whole lot of sessions for the rest of the week that will hopefully give you the details you need to be able to make your products. So in introduction, we're going to talk about sort of the design and the scope of IOKit. IOKit is just one word. It doesn't really tell you what all it covers, and it's actually important to know what fits in IOKit and what doesn't fit in IOKit. We'll talk about kernel extensions some because that's the basic unit of delivery for IOKit components. And I'm also going to spend a little bit of time talking about how applications can get access to devices. This is very important, obviously. If somebody's porting any kind of application that maybe wants to sync to a handheld device or touch any kind of hardware that's out there where a higher level abstraction is not appropriate. So we'll spend some time talking about the various models for that. So it's only a couple sessions into WWDC this year, but I'm sure you're already familiar with this slide. We're going to be focusing in on the bottom, the Darwin capsule there. And to expand on that a little bit, this is the explosion of the Darwin kernel, and there's a lot of components in there. IOKit is just one of them, and drivers are built based on IOKit primitives and provide services to the rest of the core OS, the Darwin kernel, and to higher level applications as well. So what is IOKit? There's really three views of IOKit. To driver developers, it's a framework that makes it as easy as possible to write a driver. That's our goal, is to make it as easy as possible to write a device driver for Mac OS X. And I've got in my definition here, correct Mac OS X drivers. We've had to spend a lot of time thinking about the threading model and the memory management because it's very different under Mac OS X than it was under classic Mac OS or even under other operating systems out there in the world. So what we wanted to do was put as much of that knowledge into one framework as possible so you didn't have to go and reinvent all of that. And that's one of the fundamental goals of IOKit. To application developers, IOKit presents a abstraction of hardware and a rendezvous mechanism. And by rendezvous mechanism, I mean also arbitration, where you can have one device being shared between two applications. There's higher level abstraction services built higher up in the operating system, but all of them ultimately boil down to what IOKit allows for mutual exclusion of devices. And to the OS, IOKit really serves as an abstraction of each attached device. That's sort of its simplest definition. It tries to provide an abstract object for each device attached to the system. Now, more from a development perspective, IOKit is a framework and a collection of families for developing Mac OS X drivers. Simply put, that's what it is. It's a library, but it's a very big one with a lot of APIs. It's delivered on the Mac OS X developer CD, so there's not a separate SDK or KDK that you have to download if you've got the Mac OS X developer CD. You have IOKit. Now, we will be occasionally posting updates to our website, but basically go to the CD and you'll find the developer package there that contains all of the APIs in IOKit. From a runtime perspective, IOKit is part of the Darwin kernel. It's compiled into the kernel, it executes in the kernel address space, and all of the APIs that IOKit presents are present in the kernel.framework. That is all the in-kernel APIs are present there. The applications that the APIs that we present to application developers are present in the IOKit framework. Now, the distinction here is As has been said in previous sessions, inside the kernel and outside the kernel, development environments are very different. There are different APIs, there's different rules for threading, for memory management, and as a result, we have to have two separate sets of APIs for that. The IOKit in kernel implementation is an object-oriented design based on a subset of the C++ language. Now, the application level bits are still object-oriented in nature, but they are straight C. We don't use C++ for the app-level APIs. Now, the question, of course, comes up, when do I need to use IOKit and when not? Well, if you're developing a driver that must run inside the Mac OS X kernel, and I'll spend a little more time on that later, then you're probably going to be living inside the IOKit framework. You're going to be making use of IOKit APIs. And if you're developing an application that needs to directly access devices or drivers, then you're going to make use of IOKit as well, not necessarily by subclassing from it, but by making use of its user-level APIs to get at the hardware. Now, not all drivers in Mac OS X are IOKit drivers. This is important. Most of the imaging devices, scanners, printers, cameras, things like that, are not managed inside of IOKit. We really only try to put things in the kernel that need to be there for other reasons. And I'll dive into some of these details a little bit later. The design goals of IOKit are pretty straightforward. It's a very complex task writing a driver for a system that can run on MP and have preemptive scheduling, to have to deal with multiple address spaces, and also ideally be architecture neutral, something that isn't tied to one particular platform, because as you know, evolution of platforms tends to maybe render some of those design decisions inappropriate in a few years. So we've spent a lot of time trying to hammer these things out. Drivers really focus on mechanism. When you write a device driver, you're focusing entirely on the bits of code that are necessary to push data in and out of a physical device. Ideally, we'd like to keep policy out of drivers. The idea is a driver is there to move data between the operating system and a device. And you really want policy user experience issues to be driven at a higher level. This is an important point though. Third-party developers can extend Mac OS X and IOKit just like Apple can. Through the Darwin open source community, you can download 95% of the source code to IOKit and its families. You can develop new families. You can develop drivers for existing families. It's a very flexible model, and we don't actually do anything within Apple that we make it impossible for a third party to use. Now, IOKit itself is, as I said, a very, very large framework, and it contains a lot of API, a lot of surface area. Well, just for us to be able to manage it and think about it, we had to subdivide it. And the way we did this is by dividing it into families, and then within families, multiple drivers. So IOKit in and of itself is just a framework. It doesn't have any intrinsic protocol support. SCSI is not part of the IOKit meta framework. It doesn't understand SCSI commands. The protocol specifics are embedded into families. The idea here is you would have a SCSI family that understands what it means to be a SCSI device, and a USB family that understands what it means to be a USB device. Underneath each one of those families are a collection of drivers, some of them written by Apple, some of them written by third parties, and all the device specifics are embedded in those drivers. Now, IOKit families contain classes that present an abstract view of a device type. That's basically what it's trying to say there is a family presents the abstraction of a type of device to the system. So if all disk drives fundamentally look the same, the family, the storage family, would present that abstraction, and everybody that builds a device driver underneath that abstraction would inherit from it and therefore get sort of the same appearance to the upper layers. In this way, upper level services can look and find things in IOKit in a common way. A device driver from one vendor doesn't look completely different from a device driver for another vendor if they are for the same type of device. Device drivers inherit the device independent details from the family, and then as a developer you fill in the device dependent pieces. So just to kind of give you a shopping list here of some of the common families, you can see kind of a naming theme here, and there's plenty more. This is probably a third of them. There's also ADB family and other somewhat more esoteric ones that you probably won't ever see. These are the ones I get most questions about from developers. Now, from an object-oriented class perspective, drivers in the IOKit universe are leaf classes. That is, they don't intend to have any other class inherit from them. Now, IOKit developers, the IOKit engineers at Apple who have built IOKit have had to write all their code with the knowledge that you people are going to be subclassing them. So we've had to put a lot of attention into the subclass interface. Now that takes a good bit of discipline and object-oriented experience to be able to design a class that intends to be subclassed. So fortunately, you don't have to bother with that for drivers. Basically, you inherit from something we've written, you write the bits that you need to, and you don't have to worry about third parties inheriting from you, unless you want to, and that's a whole other presentation. And your driver really should focus in on the requirements of one particular device, or possibly a collection of devices that are very similar. Now there's a data structure that's in IOKit. It actually exists in the kernel address space called the IO registry. And it's important to understand that the IO registry is not something that's brought in from a file. It's never archived on disk. It is literally the network of active IOKit objects in the system. And it's roughly a tree structure. I say roughly, if you browse it through any of our tools like IO Registry Explorer or IO Reg, it will appear as a tree structure. It is actually possible to have one node have two parents. This is done for fan-in devices like a soft RAID might choose to use that for implementation. So the technical term, I believe it's a directed acyclic graph, but basically a tree structure. Now what it does is it tracks all of the relationships between the various objects. As I said, the nodes in this graph are the actual objects that make up your drivers and the other family components. And so there are links between them. There are planes within the IO registry. There's a service plane, which is the one you'll hear about 99% of the time when you're looking at IOKit. The service plane basically says, this object depends on this other object for some service, and the service is usually named by the class name. So IO PCI device provides a service to some other driver, and the service it provides is access to an IO PCI device. IOKit tries to mimic the physical world wherever possible. Also built into IOKit is the basis for driver matching. Now, each family can override this and can change the behavior. So the example I'm about to walk through is going to be true, 99% true for every driver that you see, but there's always going to be some slight variation. So you have to check with the header files for your family and documentation that's available for whatever family you're in to understand how the matching will be different for you. It's basically 4 stages, and I'll walk through those in 4 future slides. But it's fundamentally a score system. So effectively you've got some set of drivers identified as appropriate. We use scores to try to figure out which one is best. It's very powerful and flexible. There's quite a lot that you can do to change the way that matching occurs as needed. So step 1, device discovery. This is really sort of before the matching begins, but during boot or when a dynamic bus has been rescanned, we notice a new piece of hardware. In this case, I've written it up as a PCI device discovered during boot. Well, the host controller driver is going to create a nub, an IO PCI device nub. That's a term we kind of invented that represents that piece of hardware. If there's 5 PCI devices in the system, you'll have 5 separate IO PCI device nubs, one that represents each piece of hardware. And that nub will register itself for matching. This is how matching gets kicked off. So in step 2, it's called class matching. This is something that's done basically in the IOKit innards. It's not something that the family typically alters. Basically, IOKit starts with a list of all drivers known to the system. Everything that's been installed that we're aware of. We then go through and remove kernel extensions that don't appear appropriate. First off, it would have to be an IOKit driver. So it's going to have an IOKit personalities property. And we're going to look at the IOKit provider class. That would be the name of the class for which this driver is appropriate. In the example that this is being an IO PCI device, all the contending drivers would need to list IO provider class as IO PCI device. Obviously, if it's looking for an IO audio stream, it's not appropriate to try to match it on top of an IO PCI device. So at the end of this process, the list is sorted in probe score order. Now, effectively, we have a list of drivers, any of which could conceivably talk to this piece of hardware, and based on the highest score to the lowest score, we're going to be drilling down a little deeper. So step 3 is called passive matching. We call it passive because the driver being considered isn't really running. It's not been brought into the system at that point. Its property list has been brought in, and this property list contains properties that we use to determine if this driver would be appropriate. The details of passive matching are typically family specific, but generally each family is going to put properties in its device nubs that would be useful to match on. So a vendor ID, a device ID, in some cases like SCSI it might be a manufacturer string or a serial number. All of these properties, again, you look at the family spec, but each family will publish a set of properties there that are appropriate for passive matching. The drivers being considered would also provide information in their match property, and effectively the passive matching step goes through and rules out drivers that are not appropriate. If it's a piece of hardware from one company and the driver says, I only want to match on vendor ID X, and it happens to be different, discard that driver, it doesn't match. At the end of this, probe scores may have been adjusted. Now, the device driver itself is not going to have adjusted its probe score, but the family may have. The family at this point has got a little more information than it did in the previous step. So it may have decided to promote or move down in priority some driver based on family-specific criteria. I know that the USB family implements the USB matching specification, and it does, in fact, affect the probe score. So again, we have a list sorted by score at the end of the step. Ideally, we're down to one driver, but maybe we're not. Step 4 in this process is called active matching, and it's active in that each driver is brought in and probed. So each of the remaining drivers is loaded and probed, and effectively they're given the opportunity in C or C++ code to be able to talk to the device, find out if it is appropriate for them or not, adjust their own probe score, and return. They can say, this device is not appropriate for me at all, or they can say it is appropriate, but I want to raise my probe score or lower my probe score because I discovered something about it that affects that. It's pretty rare that you would do that, but it is, as I said, this is pretty flexible. Now, all the drivers that fail their probe are unloaded at this point. They're clearly not of interest. But the remaining drivers are starting with the highest probe score and marching down the list until one of them successfully starts. In general, if you've passed your probe, you will successfully pass your start as well, so it's generally the very first driver on the list at this point. But it is possible that you discover something during start that causes you to bail on this hardware. And at that point, we have a winning driver. We have a notion of match categories that you might have noticed in some IO-Kit documentation in the tutorials or some other places. In general, you won't need to use that. I bring this up only because I've had a number of questions about it. The idea there was there may be multiple drivers could usefully be attached to one device at any given time. And the idea here is you could have one piece of hardware that maybe is bimodal. It can operate as a tape drive or it can operate as a floor buffer, whatever. And effectively, you can have the floor buffer driver be in one category and it can win for that category. And you can have the tape drive driver be in a different category and win for that category. Now, you can only typically have one driver actually accessing the device at a time, so you'd have to go through open-close to be able to actually acquire the device and use it. But that allows you to have multifunction hardware share drivers. So if you need to do something like that, if you have a really interesting multifunction device, this may be one technique you can use. So this matching process, by the way, is repeated independently for each match category. Now, developing inside the kernel is a bit of an art. It's not something that we encourage all of our developers to do. Obviously, we want the kernel to be as lean as possible, but it's also something that isn't necessary in a lot of cases. We'll talk a little bit about what it means to develop inside the kernel. For now, you have to use Apple-provided tools. If you wanted to use CodeWarrior or some other tool for that, you'll have to contact the provider of that tool and ask for that support. Apple is willing to work with other tool vendors to show them what's needed to develop in this space, but presently you have to use our tools. When you want to do debugging, you need to use a two-machine debugger. We have a debug environment that uses GDB, and it uses two machines connected over Ethernet. It's a very powerful environment. There's a lot you can do with it, but it's probably different, unless you've already used GDB, it's probably different than anything you're used to. So there's going to be a learning curve there. Once you've learned it, I think you'll find it very powerful. And the fact that you can download source code from Darwin means that you can actually do source code level debugging within the kernel. Now, we have restricted language features. Specifically, a lot of the libraries, the standard POSIX libraries that Unix programmers are used to using, aren't available in the kernel. Basically, it's a mini environment, so to speak. We would encourage you to go and look at the headers in the kernel framework to see what's available. There's also a tool called NM, which will tell you all the symbols. So if you're a Unix developer, there's some symbol you're used to using and you just want to find out if it's in the kernel, it's a very easy way to find out. Run an NM on the kernel and find out if it's there. Also, if you're developing an IO kit, you're going to be using C++. C++ is available for other types of kernel extensions as well, but it's pretty much required for IO kit kernel extensions. We don't support a full-blown C++ implementation. Our initial port of IO kit C++ was based on a movement called embedded C++ from a few years ago, and we're going to be evolving what that means to us. But basically, some of the higher level features like multiple inheritance, exceptions, RTTI, these things are not available. Also, you really need to use our constructor metaclasses. We have our own replacement for RTTI that's used to maintain reference counting and automatically unload drivers, keeps track of a lot of very important things. And if you're writing a driver and you're making use of objects that derive from the OS object class, which is the root of all our intrinsic C++ support, then you have to use the OS metaclass macros when you define a new class. I know this has not been well documented and we're working on improving that, but it is very important. Otherwise, you're going to get into situations that can cause panics and other crashes because we may decide to unload your driver because there's no references of it. Well, there are references of it, but our runtime system doesn't know that. There's very limited user interaction inside the kernel. You can't just communicate with an app directly. You have to set up explicit communications. Now, we do have some basic facilities. We have this kernel user notification center that allows you to pop up simple panels, that allows you to possibly launch an application if you needed to have a GUI. But the code that actually does that is not in the kernel. The code that would display on the screen is outside of the kernel. So you can have your in-kernel component cooperate with something out in user space, but you can't directly talk to Carbon APIs or Toolbox APIs or anything like that. Inside the kernel, resources are much more costly than they are in user land. Now, the reason this is so is because kernel memory is typically wired. If you allocate memory in the kernel, unless you go out of your way to unwire it, and that's tricky to do, that memory is wired. Now that means that that memory is permanently unavailable for other applications, other components in the system to use. If that same amount of memory is being used by some task in user space, when that task is not active, those pages will page out and that physical memory will become available for something, some other entity to use. So basically, you don't want to develop inside the kernel unless you have to. I think that's probably been made clear. The last important reason is failures are fatal. We want Mac OS X to be the most stable operating system on the planet, and obviously you want to try to contain failures. If an application crashes, we want the application to crash and not affect anything else. If you've got something inside the kernel and it crashes, it's going to probably bring the whole system down, depending on the nature of the failure. But basically, if you crash inside the kernel, you've crashed the system. That being said, if you've decided to forge ahead and write code inside the kernel, here's how you do it. You're going to have to write a kernel extension, which is basically a package for binary code to be delivered into the kernel. Now, you can write a kernel extension that doesn't exist inside one of the three well-defined frameworks, but it's not really going to do very much because nobody's going to call it. So you really are going to be looking at one of these three universes, the IOKit universe, the kernel network extensions, NKE universe, or file system plugins. The three of them use fairly different APIs, so I can't go into any specifics for the latter two. But basically the idea is the kernel extensions are there to deliver binary code into one of these universes, and then the APIs that are appropriate in that space take over from there. An extension in classic Mac OS is not necessarily a kernel extension on Mac OS 10. If you've delivered functionality in the past using an extension, it may not be appropriate to do that on 10. You need to stop and think about the best way to package your functionality. So get inside the kernel only if you have to. So a kernel extension is the way to get into the kernel if you want to do something a little bit more interesting. Kernel extensions can also serve as libraries to other kernel extensions. It's a relatively straightforward layering mechanism. So let's say that you're writing a family of drivers for your company that share a common service library. So you've got a USB version of something and a FireWire version of something, and 90% of the code is the same, but you need to have some bus-specific code as well. You can write a library, effectively, that contains that 90% common code. And then you can write a kernel extension that depend on that library for the bus-specific details. And when you've done that, you've basically just written a family. That's the way families work. They're just a library that has leaf classes plug into it. So how do you actually go about writing a library? There's really only a couple things you have to do that are unique. First off, you have to identify yourself by a CF bundle identifier and a CF bundle version. These are properties in the plist. Not too onerous. You have to do this whether you're writing a library or not. All kernel extensions have that. But you indicate that you are a, I didn't put it on the slide. You indicate that you're a library by expressing the OS bundle compatible version, which basically says this is the oldest version to which I'm binary compatible. And that is the clue to the system that, aha, this is a library and somebody could try to link against this. Somebody wanting to make use of a library indicates this through the OS bundle libraries property. Basically, you list all the libraries on which you depend when you write a kernel extension. Here's a list of some of them. The list is very long. The first 5 on this list are components of the kernel itself. You could say I depend on com.apple.kernel and pick a version number based on one that we've shipped. And that basically means you're dependent on some version of the whole kernel. Most of you won't need to do that because you're only going to be including API from IOKit and maybe from Mach and libkern as well. But basically we've subdivided the kernel into 4 other pieces: Mach, BSD, IOKit, and libkern. And you need to list these explicitly in your kernel extension when you're writing an IOKit driver. We recommend that IOKit drivers list com.apple.kernel.iokit as a dependency, as well as libkern, because that's where all the OS objects are defined, and Mach, because you're going to be using primitives from Mach for return codes and things like that. You're also going to want to list the specific family on which you depend if you are writing a driver that depends on a family, which most of you will be. So for example, if you're writing a driver for a USB controller card that sits on a PCI bus, you would need to include the PCI family and the USB family. They're the 2 families that you depend on. So now to actually talk about kernel extensions and how they exist on the file system, we've got a series of slides here that explodes it. If you look at this, this is a directory hierarchy, and you'll see that there's only 2 files in here. The rest of it's all structure. We basically chose to mirror the application bundle format because all of our tools are there to deal with it. Finder already knows how to deal with these, and they have some nice features about them. It's probably a little bit more than strictly necessary for delivering drivers, but it doesn't really cost anything. So there are really 2 files in a typical kernel extension that are going to be interesting to you. The first one is this info.plist. Every bundle of any description on Mac OS X has one of these files. And basically it is the table of contents, so to speak, for the kernel extension. It provides information on what it is, why it would need to be loaded. This is where the IOKit personalities with the matching information goes. So I've listed 4 basic properties here that are pretty much going to be necessary for all IOKit drivers. CF bundle identifier identifies your driver. Now, we've gone with a reverse DNS namespace because this doesn't really require Apple to put some kind of a program together and police it. Basically, if you can sign up for a domain name, put it in reverse order. So for Apple, we ship drivers and other components under the name com.apple.whatever. Obviously, unless you work for Apple, you shouldn't be doing that. You should be providing your own company name there. And once you get within your company domain, you can decide whatever namespace within that you want. So it's actually pretty flexible. It tends to be a little verbose, but that's okay. This information is usually only thrown around when we're loading drivers. Once they're loaded, it's just sitting around as information. Your CF bundle version is also going to be important. Our version checking code makes use of this to know that it's getting the latest and greatest piece of software. So right now, the format is specified as a classic macOS VERS resource, something you're probably familiar with already. OS bundle libraries, this is where you list all of the libraries on which you depend. So com.apple.iokit, whatever family, all the libraries that you care about. It's very important to understand that macOS 10 as it's shipped so far doesn't enforce all of these properties. It makes note of them and it does its best to use them, but we didn't have time to get all of our drivers into compliance, so we have to allow them to be a little bit fuzzy. Future releases of the macOS 10 operating system are going to require that these be in order or your driver will not load. So, for example, if you don't have a CF bundle identifier, it won't load. I don't think it would load today, actually, because that's key to a lot of things. If you don't have a bundle version, it won't load. If you don't list any bundle libraries, it won't load, because by definition, if all you're doing is calling into the kernel is acting as your library. You have to list at least one thing as a dependency. Otherwise, your kernel extension could not call any API. And if nobody is calling you and you're not calling anybody, it's kind of a useless kernel extension. And the fourth property here, IOKit personalities, this is the only one that's IOKit specific. This is where you would list all of the personalities of your driver. This is a little subtle. By and large, your drivers will have a single personality. That is, one set of matching criteria, a few properties to help your driver get oriented when it gets loaded. But you could also have multiple personalities. You could have, say, 2 PCI cards that you ship that are similar but slightly different, and they need different match criteria. Well, one driver could drive them, but you could list 2 personalities, one for each of those flavors. It's very powerful. We use this ourselves. We have several multi-personality drivers. As a very useful resource, go into the extensions folder on 10 and poke around and see what's there. Though I will warn you, as I said, not all of our drivers are in spec, so we'll also look at the log that comes out and see all the warnings that get posted. The warnings are on our drivers as well. So. The next file that's important here is the binary that the Kext is delivering. In this case, I've exploded the USB family, but this is the actual binary file. First and foremost, it's optional, which may seem a little bit odd. Since the kernel extension is a way to deliver binaries, what does it mean to have it be optional? We have a notion of a driverless driver that is used occasionally, and this is where personalities come in. In your personality, your IOKit personality, you will specify the class, the basic class for your driver, and you'll also specify the CF bundle identifier for the kernel extension that contains the binary code. You could write a driver that depends on some other driver and actually just instantiates its classes directly. There are a few cases where this is useful. Basically, you would put in some new property in the personality. Maybe it's as simple as changing a probe score. I want to use this driver over here, but I want to make it slightly different matching, and I want to have a higher probe score. Okay, enough said about that. If you do have a binary there, it's going to be in the Mach-O format, which is the only format the kernel will load presently. And please run strip-x on it before shipping it. I've looked at some of the drivers that have been posted. Obviously, I'm interested. And some developers have forgotten to run this, and it means that their download size is about 10 times larger than it needs to be. And they're giving away all their debugging symbols. It doesn't affect the runtime at all. We only load the important pieces into the kernel. But if you want to have faster downloads, strip-x is a good thing to do. Okay, last is this plugins folder inside the kernel extension contents. And this is kind of neat. Again, it's optional. If you have a plugins folder, it gives you a place to deliver other kernel extensions. The reason you'd want to do this is for the drag and drop functionality. Let's say you've got a collection of 3 or 4 drivers that you always want to move around together as a collection. What you can do is pick one that is sort of the definitive Kext, and then put all of the other pieces as subkexts, as we call them, inside the plugin folder. The advantage there is to the user, it appears to be one kernel extension. To our loading system, however, we consider every kernel extension equal. So we don't care whether it's embedded or at the top level. That's actually important to note. The fact that it's embedded doesn't mean anything at all. It's just a way to deliver it. Now, the plugins folder can contain other kexts. It can also contain device interface libraries. This would be typically if you're writing a driver with some sort of a custom interface that applications would need to get at directly, or if you're writing a family and you want to provide a user client or a device interface for an application. That's a handy place to store the bundle for that. And in the future, there'll probably be other things of interest that could go in that plugins folder. It's sort of a generic place to put add-ons. Only one level of nesting is supported, though. You can't have a kernel extension inside a kernel extension inside a kernel extension. Well, we could have made this work, but there was very little use for it. The user sees the top level. That's our intent. You can package things internally. If we want to have more complex relationships and organizations, send us notes on how you'd like to have that done. I don't think creating a massive tree inside the extensions folder is necessarily the right way to do that. All right, now I want to talk about the user kernel boundary. This is new, I think, to developers just coming in from 9, looking at 10. There are different places on macOS 10, different address spaces. Drivers live inside the kernel. Applications live outside the kernel. So anytime your app needs to talk to a driver, you've got to cross that boundary. It's as simple as that. There's no way around it. macOS 10 and the Darwin kernel and infrastructure provide a large number of ways to get across that boundary. If you can use a sufficiently high abstraction like a file system, the file system provides that bridge for you. It makes use of BSD to cross that bridge and get data out of the kernel and into your application. Networking, sockets does that for you as well. But if you can't use a high-level abstraction and you have to use a low-level abstraction, you've got to get directly at a device, you can use, basically it's a CF plugin interface that we use called a device interface. Oh, and the class, for in-kernel class that you derive from is IO user client. The name derives from the fact that from the kernel's perspective, the client is a user. Therefore, the object is a user client. So your code belongs outside the kernel unless you must process interrupts. If you have to get at an interrupt, you need to be inside the kernel. Unless you have to deliver services to an in-kernel component. For example, file systems live inside the kernel. So if you're writing a disk driver and the disk is most likely going to be used by file systems, it makes sense for that driver to live inside the kernel. It is possible, of course, to put almost anything you want outside the kernel, but then moving data means more user kernel boundary crossings, and that costs a lot of time, so you're not going to get a huge amount of performance. But if it's a really slow device, you can have drivers live outside and tunnel back and forth across the user kernel boundary. The other reason for putting something inside the kernel would be if it provides a service that's needed by a large number of clients and it's needed much of the time. Now, this is kind of a judgment call here, but basically the kernel is sort of the only guaranteed rendezvous mechanism on the system. An app running in Darwin or Cocoa or Carbon can pretty much guarantee it's there, and there are APIs to get at it. So if you've got a service that's available inside the kernel, it's a convenient rendezvous mechanism. But if you only have one client that needs to get at your device, or if it's only used 1% of the time, why put it in the kernel? That memory is going to be used all of the time, not just when it's in use. So an example there might be a backup driver, a device driver that's only used to do backups. Most people aren't backing up all of the time. You could have one application that could load such a driver when it needs it, or it could process it in user space, and then unload it when it's no longer needed. So the device interface model, this is sort of the app view of IOKit. The device interface model provides API access for many devices in the system. It doesn't provide access for all devices. This is important. We don't provide access for applications to directly get at the PCI bus. We do let you get at devices hanging off the PCI bus, so if you've got a SCSI controller there, you can talk to the SCSI bus, but you can't talk to the PCI bus. It's actually a security issue there. Also, there are some devices it really doesn't make sense to get at from user space, so we don't create the ability to cross that boundary for every kind of device. but the ability is there if we need to make use of it in the future. The device interface model wraps a number of mock mechanisms. Basically, since mock is the IPC model, everything that we do is simply a wrapper for that. And our idea there is for IOKit to make the most common uses of the mock infrastructure easy to use. IO user client provides this. So system calls, mock traps, which are kind of similar, mock IPC, and mock shared memory. All of these mechanisms are available in the IO user client class, so if you want to set up some private communication, you can make use of any or all of these as it makes sense. So to a driver, this boundary crossing layer really looks like an in-kernel client, a subclass of IO user client. The object IO user client is inside the kernel. It's talking to the driver like any other in-kernel component. It's just moving that data across the user kernel boundary as its primary goal. To an application, it looks like typically a CF plugin, generally Mach-O binary. That's the preferred format. But basically, it is there's proxies in both space. The proxy in the user space is a CF plugin, and the proxy in the kernel space is an IO user client. They're geared to talk to each other, and your app talks to the CF bundle, a CF plugin, and the IOKit driver is going to talk to the user client. So I'm going to go through a 4-step sequence here of how this works. So from an application, the first thing to do is find the device of interest. And the way you do that is by searching the IO registry. There's a number of different ways to search the IO registry and discover the device or devices of interest. But probably the most common and most useful one is IO service get matching services. This basically allows you to find all of the instances of IO SCSI device or all the instances of IO USB device. And you can provide some further match criteria that is driven actually very similarly to the way driver matching works. But basically, you find the devices of interest, and you get a list back, and you use IO iterator next to actually walk through that list. And when you find the device you're interested in, you make note of it. And in step 2, you're going to need to call IO create plugin interface for service if this is a CF plugin style user client. The technique here is to take the cookie that you got from searching the IO registry and request a session here. So you basically create a plugin interface. This loads the CF bundle into your application, and then you call query interface, which actually returns an interface to the desired device. All right, at this point, you actually don't own the device. You just have an interface to the device. This is IOKit has multiple layers here because we also have multiple clients competing for devices. They might all want to have a session going to the device, but they don't want to keep it open all the time. They want to be a good citizen and close it periodically to allow others the opportunity to use it. So in this case, the details are family specific, but basically it follows a pretty basic open IO close procedure here. There's nothing really surprising there. Ideally, you call open as late as possible, and you call close as early and as often as possible, because as long as you have a device open, nobody else is going to be able to get at it. Each family will instrument its own arbitration policy, but in general assume mutual exclusion unless you've heard something else. And ideally, if you're doing something to a device that only takes a few seconds, open it, do that I/O, and close it. You only keep it open if you really need to, because it's in some volatile state that you can't easily restore, or it doesn't make sense for it to trade owners briefly. And the last step is to release the interface to the device. This just cleans things up. If your app crashes, this gets done for you. But ideally, you explicitly clean this up. There is a release note. I'm sorry I don't have a more specific reference, but if you go to the ADC website, you should be able to search for this and find it. CF Bundle and CF Plugins release note describe a lot of the APIs, the app-level APIs. Now, I want to talk for a little while about the different app models. I gave you a rundown of how to do that, assuming that your app could talk to a Mach-O plugin. But there's a number of different application spaces on Mac OS X. So for starters, let's take a classic application. Well, there's no direct IOKit access for a classic application. It wouldn't be a compatibility environment if it included all the IOKit APIs. So basically, whatever is present in classic, whatever abstractions are there, that's what you get. All communications go through Classic itself. The same is true for a pure Carbon app. If you're writing a Carbon app in CFM and you're keeping it pure, you're only calling Carbon APIs, you only get what's in Carbon. And that's kind of the definition of a pure Carbon app. So you go through the Carbon framework, and that's how you get down into the kernel and get at drivers. But there's not a tremendous amount there. Now it starts to get a little bit more interesting when you are willing to do macOS 10 specific code in your application. And in this case, we've got a CFM Carbon application which has basically two ways to talk to IOKit. One is through Carbon in places like IOSCSI Action, where we've actually provided some Carbon APIs for device access. You can make use of that. But you can also make use of the plugin architecture that I described in the previous slides. Now the coloration here is a little bit of a giveaway. The orange represents parts of the Darwin kernel, things that Apple provides you. The purple is the app environment that you're using, and the blue boxes on the top are the boxes that represent code that you write. You write the application itself, and you write the CF bundle that provides the interface down into IOKit. Now, this is actually kind of handy because it allows you to write a different plugin for running on macOS 9. So you can write one application that runs on 9 or 10, and it would load a operating system specific plugin to do its I/O. Now if you're writing a Mach-O Carbon app, it actually eliminates a layer there. You don't have to have the plugin because you're not switching over from CFM to Mach-O. You can directly call the plugins that IOKit provides. And of course you can still go through the Carbon environment. That's always available to you. And the same is true for a Cocoa app. Basically you can go through Cocoa or you can go through the CF plugin. What I don't have up here is a pure BSD application, but a BSD application has all the CF plugin stuff available to it, plus all the BSD APIs as well. So I don't have any other details on IOKit for you today. What I do have is a rather lengthy roadmap for other sessions, because that's where the details are going to be conveyed to you. There's sessions on graphics, actually right after this session. There is sessions on image capture, sessions on input devices, FireWire, USB. Spend a little time looking through your guide if you haven't already, and figure out which ones are going to have information most relevant to you. There's a lot of details. There's a lot of API that fits under the IOKit umbrella. And yet another page of them.